Hello. Okay. All right. Mic check. All right. Welcome to lecture 12 of class CS 176B. Today we are going to talk about sketch-based telemetry systems. So let's try to recall what we learned in the last class. We talked about network telemetry systems in general, and the goal of these telemetry systems is to ensure or provide network operators with the insight about what's going on in the network, right? So they can detect a wide range of network events. There are a lot of requirements from the telemetry systems, but two key requirements that we discussed were flexibility and scale. When we talk about flexibility, it means that these systems should be able to, or should enable the network operators to express which type of metric they're interested in and from what portion of the traffic they want to extract that insight, right? And they should also provide this flexibility such that the result of one analysis can be combined with the other, so that you can, take the result of one analysis, combine that with the other. Is thinking, you can think about it as, set of features that you're trying to extract from the network, and then you can combine those features together to draw or to make some bigger inferences about what's going on in the network. In terms of scale, we talked about the requirement that these systems should be able to scale the execution of multiple queries or queries for multiple tasks, such that they can, compute or execute these queries for high data rates, though there will be limited compute memory and bandwidth resources available in the network, right? So given these constraints, the scalability challenge is to make sure that they can scale the execution of all these queries in parallel for high data rates. Sonata is one system that we covered in greater details. Sonata is a hybrid network telemetry system. What does hybrid really mean here? So we'll talk about it. But Sonata is a reasonable system because it offers some flexibility. It enables them to express monitoring tasks for a wide range of network telemetry tasks as data flow queries. It is scalable because it iteratively refines the queries and partitions them between the data plane and the user space target, right? So it is trying to make the best use of the limited resources that we have across two different type of targets for query execution. So I decided that in this lecture, we'll try to dig a bit deeper into the design spectrum of telemetry systems, right? So that we can better appreciate where Sonata fits into the picture, versus where the Starflow that you have already read as part of the reasoning assignment, where does that fit into the picture, versus the sketch-based solutions that we're going to talk about today, right? So I wanted to do a bit of a deeper exploration of that design space, and then that way you will be able to appreciate more that where, what are the pros and cons of different systems. And then later, when you have to build your own network telemetry systems or whatever enterprises you're working on, I think you'll have a better judgment of how or what factors to take into consideration when you design those systems. So before we talk about the design spectrum, I want to revisit this slide that we covered in the last lecture as well. So we talked about two different type of targets that we have available for executing queries, right? One is the general purpose CPU that we can use. The other is a set of switches, right? Programmable switches. CPUs are great because they offer a lot of flexibility in terms of what type of fields you can match on. So you can easily define what portion or what subset of traffic you're interested in. The actions, you can do whatever transformations you want on the packet. So you can, extract whatever metric you are interested in if you're doing this processing in this general purpose CPU. And also there is no restriction in terms of amount of state that is available because you can use DRAM. So DRAM is relatively cheap. You have gigabits, sometimes terabits of RAM available, DRAM available. Like those terabits will be expensive, but theoretically that's possible. The challenge is the speed that it entails multiple CPU cycles to execute or process given one packet in the user space. So the time it takes is of the order of microseconds, right? And that's a bit of a challenge. The switches, on the other hand, are very good in terms of speed, right? So if you can compile a program in P4, then you can guarantee that that packet will get processed at line rate, which is of the order of few nanoseconds. But switches have constraint in terms of other resources, both in terms of the amount of memory that they have, because you will be at best be using SRAM. So SRAM, even though it's cheaper than TCAM, but still it is an expensive resource. You can only match on header, a subset of header fields, most of the header fields, but few other meta header fields as well. But more importantly, the type of transformations that you can apply on the packets are relatively limited, right? So you can only do add, subtract, or maybe bit operations. So switches do offer limitations in amount of state, in amount of computational prowess that you have. But at the same time, they're very good targets if you want to, do this fast processing, right? So this lays out a different type of design choices that you have, and we will go through this design spectrum of telemetry systems, taking these factors into consideration. So let's talk about first type of network telemetry system that a lot of you are, like in general familiar with it because you've seen Wireshark and other tools. So the idea is that these switches, they will write a program which will say, like, all the packets that are coming in on a set of interfaces, they will be sent, cloned and sent to a mirror port, right? So when you clone these packets and send to a mirror port, then you're not affecting the original network traffic, and then you're able to capture all the packets that you see in the network, right? And this is something which is very, very valuable, right? So for example, a very simple example of this is that when you run the Wireshark tool on your laptops, right? So the Wireshark tool, what it does is that it sniffs the packets coming in on a particular interface, and then it is pulling those packets from the Linux kernel and putting it in your Wireshark program, right? So those packets are cloned packets, right? These are copy of the original packets. The original packets are received by your specific applications running on your laptops, and that's why those applications are working. Or when you run these Wireshark tools, it's not that your other applications stop working, right? So that is an example of full packet capture. Of course, you can specify a set of filters that you want to apply and all those things, but still, this is clearly a very expensive thing to run. And there are a lot of systems designed around this idea. So these systems are, I wouldn't say they're like completely impractical systems. Gigascope was a very practical system that was developed by AT&T, but that was developed in 2003, right? So this was a time when the data rates were relatively low, or the volume of traffic in the network was relatively low. But still, it had scalability issues. It had a lot of interesting optimizations in terms of how it was doing the packet processing in the server. So, it had some distinction about what set of operations it can offload to the fast path of the server, and what type of operations it has to run in the user space. So Gigascope was an interesting system, but it was around the spectrum, part of the spectrum where we were doing the full packet capture from the network. NetQRE is a system that was developed by folks at UPenn around 2017. And the key idea there was that they were trying to do, supporting regular expressions on the network traffic. But the system was very powerful and flexible in terms of what type of operations you can do. But the scalability challenges were limiting the system in terms of scale. You cannot say run this type of system for 40 or 100 Gbps link, right? So clearly, this type of approach is very flexible and accurate. Accurate because you have all the packets. So whatever queries you run on the data that you have collected, the output of the query will be very accurate, right? Like you won't be compromising on accuracy. It's very flexible because you have all the packets at disposal, so you can express whatever queries you want to run, right? The downside, as we were discussing, is the scale. It has a high bandwidth storage and a high storage footprint. High bandwidth footprint and a high storage footprint, right? So bandwidth footprint, it is intuitive that if you have a 100 Gbps link or 100 Gbps of traffic coming into the switch, and if you are capturing each and every packet, then you need a bandwidth provision of 100 Gbps so that you can push all those packets to a server, right? So in general, your bandwidth capacity at the switch is halved, because if you're capturing all the packets, right? Because you need this similar amount of bandwidth to move the packets from the switch to the server, right? And also it has a very high storage footprint in addition to so many other footprints that has. You can see that for a 100 Gbps link, if you collect this data for 1 hour, you'll be looking at a footprint of 45 terabytes, right? And 45 terabytes might not sound a lot of data, but it can be very intimidating data if you are, say, a network operator at UCSB, right? So this is a huge storage footprint. And this type of setup is very good if we are interested in, like small scale analysis, or if you're interested in, security focused, forensic analysis, but it is definitely not suited for real-time query execution. But before I move forward, I also want to emphasize that this is kind of like, the ideal system that you want to build, right? You want to not compromise on flexibility and accuracy of the queries that you can run, but at the same time, you want the system to scale. This approach does not scale, but if we can figure out ways in which the system can scale, that will be awesome because we don't have to compromise on the flexibility and accuracy of the solution, right? So keep that in mind when we think about the design space in general. So moving on, the other side of the spectrum is where we can, use these programmable switch and try to run the query execution completely on the switch, right? So what we are sending from the switch is the output of the query or process metadata of the query to the server. So clearly the overhead at the server is minimal in this case, right? But the downside is that it offers limited flexibility because it can only support the set of queries that can be executed in the data plane, right? So if there is a type of query that cannot be compiled in the data plane, then you cannot support it, right? Also, the scalability benefits are limited. So even though you are compiling the query in the data plane, but because you have limited resources in the data plane, then you have to compromise in terms of how many queries you can run or for what volume of data you can run those type of queries, right? So just to build some intuition, if there is a link with 1 Gbps of traffic, and if you apply a stateful operation, say distinct or reduce, as we were covering earlier, versus the link which has 100 Gbps, then you would expect that the 100 Gbps link will require a lot more state to perform the stateful operation, right? And depending on how much resources we have on the switch, this type of scaling might or might not be possible, right? So that is one example, but then also think about the cases where you are trying to execute or compile multiple queries at the same time. So for example, if you have 10 different queries and each of them requires say 4 megabits of memory, then you will require 40 megabits of memory in the data plane, and probably for a lot of use cases or a lot of cases, you probably won't have this much memory available in the data plane, right? So these are some cases, but these type of systems are very good if you know that you only need to run a very small subset of queries. This is fantastic, right? And of course, if you directly use the hash tables, or if you use or execute the stateful operations as hash tables, then you will need a lot more memory, as we discussed in the last lecture as well. So one approach that Sonata explored was that it was trying to do the iterative refinement, right? So it was trying to reduce the memory footprint by iteratively refining the query. The alternative approach, which came before Sonata, was to use sketches for stateful operations, right? So if you want to do reduce or a distinct, rather than using an exact hash table, you can use an approximate data structure, which is called sketch. And that will help us reduce the memory footprint for executing these queries. So OpenSketch came out in SIGMOD 2003. I think there is a problem here. I think like OpenSketch probably came out of SIGCOMM to 2013. So there's a mistake here. But this was first of its kind paper, and that's something that we will cover in this lecture as well. Universal monitoring was a follow-up paper that we will also cover in today's lecture that was presented in SIGCOMM 2017. And then OmniMon is something which was presented in SIGCOMM 2020 itself, and that kind of tries to generalize these sketch-based solutions in general. So we will talk about these solutions, but I just want to give you an intuition that the design spectrum here is that you do everything on the server versus you do everything on the switch, right? So the OpenSketch, universal monitoring, all sketch-based systems kind of like fall into the category where we try to execute as much as possible, or we try to execute the entire query in the data plane itself, right? So this type of system is definitely not suited for executing multiple complex monitoring queries, right? But that, given those limitations, it's a reasonable trade-off if you have very simple queries to run. So there is another set of solution where you can be a bit smarter about what you collect. So rather than sending in the entire packet, you can say that, hey, I don't really need to look into the payload fields of the packet for most cases. So I can maybe remove those payload fields, right? And send only the headers to the server. So this can definitely help with the scalability if you just have one switch to worry about, right? But in a lot of cases, especially if you're trying to debug what's going on in a network, which will have multiple set of switches in place, so the complexity, the overheads will grow significantly high if you have that type of environment, right? So this type of approach, similar to the setup where you are collecting all the packets or doing the full packet capture, then this is definitely flexible and accurate. But this is also hard to scale, right? Even though from 45 terabytes that I was mentioning earlier, this can be as low as 10 terabytes, but that 10 terabytes is still very high, right? So this is not really suited for real-time query execution for the reason that you'll be collecting a lot of data. and then executing, running the query on top of that much of data is relatively expensive. But if you are a huge cloud-based enterprise, then you can do it, right? And Everflow and DShark are two examples of that. Everflow came up in SIGCOMM 2015, and this was developed by a team at Microsoft. In fact, if I'm not wrong, one of the lead author on this paper was a graduate from UCSB, right? So Yibo was the name of the author, and he built the system Everflow, of course, with the team at Microsoft. So the key idea there was that they were using the OpenFlow switches to apply some basic filtering of the data in the data plane itself, right? Or packet traces in the data plane itself. So that was helping reduce the amount of data that needs to go from the data plane to the user space, right? And of course, for the reasons that we were discussing earlier, this is a very expensive setup to build. It has a huge storage and bandwidth footprint. But companies like Microsoft were interested in getting this type of insight from the network, so they were willing to put that investment in place, right? And then DShark, which came out in SDI 2019. So DShark was an improvement over system like Everflow, but the DShark's main focus was to take into consideration that a packet that is traversing a network will have different type of transformations, right? So and then you want to see the trajectory of a packet within a network to do a lot of debugging. So DShark basically came up with a lot of interesting design choices that enabled that deciphering of the path of a packet or the journey of a packet in the network, right? So let me try to unpack that a bit more. So think about the setup that we discuss in systems like Espresso, right? So in Espresso, the packets that were leaving the server were first getting encapsulated, like there were two layers of encapsulation in that packet, right? And then they were going to a bunch of aggregation switches. From the aggregation switches, they were going to these switches at the edge. And then at the edge, using one of the encapsulation layer, it was deciding which port the packet has to be forwarded to, right? So whenever you capture this packet at different portions of the network, the set of fields that you will see in the header will be different, right? So if I want to debug what is, what is the performance of a particular packet across these different elements in the different components of the network, I want to make sure that I can reason about the packet across different type of encapsulations that the packet will have, right? So this was primarily the focus of DShark, that it was trying to, provide ways in which we can join the data packets seen at different portions of the network, such that we can accurately debug what are the factors or what are the network events that are affecting the performance degradation or performance of the network in general, right? So DShark is a very interesting paper, and I think it is built up on the same idea as Everflow did, that you can capture the interesting insights from the packet, all the header fields and stuff, and then do some transformation on the collected data such that you can do this type of tracking the journey of a packet in the network, so that you can use that type of trajectory to understand the state of the network more effectively, right? So this is one spectrum. Now within this spectrum, I think the another set of systems that came out were systems like Marple and Sonata, which we discussed in the last class as well. So the key idea here was that rather than trying to just use or just execute the entire query in the server or the entire query in the switch, it was trying to partition the query, right? And it was different from systems like Everflow and DShark, because it was trying to execute some stateful operations itself, or like portions of the query itself in the data plane, right? Which was not the case for the other systems, right? And so it was also able to support a broader spectrum of queries, because its query execution is not just limited to data plane, right? So unlike systems like OpenFlow and OpenSketch and universal monitoring, the set of queries that Sonata can support is broader, right? But it's a reasonable system. I might be biased because I built it, but at the same time, there are a lot of challenges with this system before it can be ready for production deployments, right? So there are some ongoing efforts going on at Microsoft and Alibaba to deploy Sonata in the production network. But in my opinion, from research perspective, there are still few challenges that need to be addressed. One, that the query planning part of Sonata is relatively complex, right? So the query planning entails understanding what type of memory requirements a particular query will have, for different levels of granularity that it is going to get executed, it can possibly be executed at. And second, the Sonata is not designed for distributed settings, which is kind of the most common case that you will see in these networks. But Sonata is is a simple instantiation of the idea, and it is not fully operational in a sense that it is not designed for these type of distributed settings. And the challenges of transferring or transforming Sonata for these distributed settings is relatively non-trivial, right? So I won't say that, hey, it's a very low-hanging fruit and it's just something that needs to be done. That's not the case. It requires a lot of answering a lot of complex research questions before Sonata can be generalized for distributed settings, right? And similarly for the query planning part, I wanted to also mention one thing, that the query planning is dependent on estimation of cost, but those estimation of cost are also dependent on the dynamics that we see in the network, right? So in realistic settings, you might want to change the set of queries that you want to run over time, or the traffic pattern or the traffic workload that is coming in at these switches might also change over time, right? So given those, how do you come up with query plans that are generalizable, robust? That is a very important and interesting research question that needs to be answered. And that is something which my graduate student has been working on. And maybe we can have a lecture of him talking about these nuances of the solution and how Sonata can be improved such that it can be useful for production settings, right? So Marple was also a system which came out around the same time. So Sonata and Marple kind of came out. The first idea came out in Hotnet's 2016, right? And then both these papers kind of got published at different times. But Marple's idea was it didn't focus much on the query planning part, right? So it focused more on executing the stateful operations as caching functions. So if you can, you try to fit as much as possible in the data plane, but when you don't have space, then you do a cache miss on engage an eviction policy in place so that you can leverage both the data plane resources as well as the server or the user space resources in a bit of an elastic way, right? So Marple is a very clever solution, very interesting solution, but it has some limitations in terms of what set of queries it can or cannot support. So now that you have some background on the design space, I also want to put forward the Starflow paper that you folks have read last week as part of the reading assignment. I am sure you have, when you read that paper, you had a different view of what I'm going to talk about right now. But in my opinion, the Starflow approach is that it is trying to apply some type of compression in the data, right? So it has this notion of group packet vector, which focuses on the fact that there is a lot of redundancy if we keep state of each and every packet in the network, right? So it tries to group them in a certain way such that we can have a lossless compression of the data in the network, right? And then rather than reporting all the packets similar to what Gigamon or NetQuery does, it reports a compressed set of data to the user space. And then the user space programs are responsible for executing the data on this compressed, or executing the queries on this compressed data, right? So the good thing about such a system is that it is definitely better than Everflow, NetQuery, DShark in terms of scale. Also, unlike Sonata, there is no query planning, right? The downside is that it is relatively, the Starflow solution as is offers a bit of limited flexibility because it limits the set of fields that it will compress from the network traffic, right? Also, the efficiency of the compression schemes are relatively limited, which means that that even after applying this group packet vector compression, the amount of data that is sent to the servers or the user space is still relatively high, right? So there is a lot of improvements that can be done to a system like Starflow, but in my opinion, it's an excellent idea, and it offers interesting trade-offs between the flexibility of the schemes as well as the scalability of the systems that you can build, right? So I hope with this background, you were able to contextualize the entire spectrum of network telemetry systems, different design choices that people have made in the past, and how do you reason about which approach is better than the other, and in across what dimensions. So now we will focus on specifically one type of network telemetry system called sketch-based telemetry systems, right? And as we discussed, the key idea here is that the most of the query execution happens in the data plane targets. and the output of the query is sent to this user space server, right? And we will be focusing on these three set of servers, three set of papers. So like especially the first two, open sketches and universal monitoring, right? So open sketch was a SIGCOMM 2013 paper, and universal monitoring was a SIGCOMM 2017 paper. So software-defined traffic measurement with open sketch was a paper published by researchers at USC and Princeton. I think I'm looking at it, and I think now all the three authors, their affiliations have changed. So Milnan is a faculty now at Harvard. Lavanya was a grad student at Stanford. I don't know where she's now. And Rui, I know, works at Alibaba, right? So crazy how things change over time. But this was a very, very interesting and powerful paper at its time. So let's try to see why, right? So the key idea that we've been talking about for the sketch-based telemetry systems is sketches, right? So now you might be wondering what a sketch is. So a simple way of expressing sketch is that it is a sketch of a data stream, right? You can think of that as a compact summarization of information that is there in a stream of data, right? So sketches are like beyond network telemetry. They are very powerful data structures that have been used, especially a lot in the area of machine learning recently, when you're trying to, perform a wide range of stateful operations over streaming data with very limited resources, right? So sketches are very good summary or compact summary of the data, and there you can also think of them as a randomized projection of a signal, right? So that uses like this projection is done using the hashing, and there are different types of sketches that have been developed over time. And I'm doing a disservice to this area by just naming four, because this is an area which has been very active in both computer science theory areas as networking, as well as machine learning these days. And there's a huge spectrum of work in the space, and I'm very, very narrowly focused on a very small subset of sketches that are very popular in the networking community, right? So Countman sketch, which came out in 2013, is very popular. Then Bloom filter, you probably have heard of Bloom filter in multiple cases as well, and then multiple count, like so count Bloom filter and multi-count Bloom filter. These are two different data structures. And then Fluglet Martin sketch or FM sketches, right? So as you can see, there is a one paper came out in 85, and there was a lot of work in 2003 and 2004. And the sketches were very popular in terms of theoretical exploration. But I think I would say around 2013, 2014 time period, there was great interest in these sketches for the reason that P4 or the PISA targets that were coming out around that time offered a great amount of flexibility in which a wide range of sketches can be implemented in the data plane, right? Before that, with the OpenFlow era as well, that's where the open sketch idea or paper is focused on, offered interesting ways in which we can compile multiple sketches in the data plane, but still had some limitations, and that's something that we will read now. But I would say that universal monitoring that came out maybe in 2016 or something, or 2017, was a very interesting paper for the reason that it offered very compact sketch representation that can be compiled in a P4 or based, like using P4 language on a PISA-based switch, right? So let's try to move forward with the sketches with some history and context in place. So Countman sketch is very popular data structure. It maintains an array of width W and depth D. It hashes by choosing a hash function uniformly at random from a pairwise independent family of hash functions. So those hash functions it is trying to use are kind of like from a pairwise independent family, right? So the way it works, I would get away with this maths here and focus on the key idea. So whenever a packet comes in, whenever like a key comes in, and for that key you're trying to maintain the count, right? So what you will do is that you have these D different set of arrays. For each of those D arrays, you will apply a hash function, right? So you will say for if it is the first array, then you will apply h1 on the key, right? And that will tell you some index of that array, and that for that index of the array, you will update the value, right? So for what is incoming for you is a key value pair, right? So for that key, you apply hash1, hash2, hash4 all the way till hd, right? I think there is a mistake in the slide here. So the last h should be hd, not hh, right? But point being that you will compute d different hash values, and based on those hash values, you will have the indexes within these arrays, and you will update, use the value, and then update the hash values here, right? And you will keep on doing for the entire stream, and at the end, what you will do is that you will retrieve for every key, you will retrieve the hash value across all these locations, or all these different D registers, and then pick the one that is the minimum across all of them, right? So the intuition here is that if you pick the minimum, then you will be bounded by, there is a theoretical bound that is proven based on the W and D that you set for these Countman sketches, that gives you provable guarantees about or provable bounds on the error, right? And that is the beauty of the Countman sketch, because you can choose to configure these sketches such that you can have some provable bounds on the error that you will get on the count values eventually. So let's move on. OpenSketch was an interesting paper that focused on, as a Countman sketch is just one type of sketch, but there are so many different type of sketches out there. And what OpenSketch was arguing is that, similar to what Sonata was also arguing, it said that it is possible to express the network telemetry task as SQL-like queries, right? Where you say, you can use these clauses of select, from, where, group by, etc., right? And the key idea that OpenSketch was arguing is that you can use sketches to apply or implement the group by clause in these languages, right? And the classifiers or the match action table entries that you have in the data plane can be used to satisfy or execute the where clause, right? So in some sense, you can think of the OpenSketch as one of the precursor idea for Sonata, because Sonata came very late into the picture compared to these systems, right? So these systems already had some built up in place where they were arguing that, hey, you can operate on all these packet fields, and you can apply this SQL-like language or use a SQL-like language, where important clauses or critical clauses like group by can be executed using the sketch data structures, and the where can be implemented using the classifier, or you can think of that as the match action DKIM entries, right? And also to put things into perspective, the Sonata does not use sketches, right? It can, but it does not. So I think one improvement for Sonata in the longer run can be that how can it use these sketch-like data structures for executing group by operators in the data plane, or any stateful operator in the data plane. Right now, it just uses hash tables, and those are vulnerable to hash collisions in general. But I think we're coming up with sketches for approximating the stateful operations will be very interesting contribution to Sonata in general. But that's non-trivial, and that's something, if you are interested in, reach out to me. I can tell you why that is very difficult to integrate sketches with Sonata. But overall, it's an open research problem that I would encourage people to venture into in the future. So clearly, this system is using sketches as the building blocks, and what it showed back then was that there are so many different type of interesting network monitoring tasks that can be expressed using this language or using this abstraction. And then I also wanted to draw your attention to this use case called super spreader, or DDoS, which is exactly the same query that we covered in the last lecture, where we were interested in finding out these DDoS reflection attack victims, or the opposite of that is a super spreader victims, right? So the goal here is to find a k super spreader. A k super spreader is a host that contacts more than k unique destinations during a time interval, right? So you have a window, you have k unique destinations that it is trying to reach out to, and rather than this is a complementary to the DDoS query that we were looking at, where the victim is a host that is contacted by more than k unique sources, right? So the reflection attack that we covered in the last class, right? So for this query, if you remember, in our case, we were talking about a distinct operator, which will take the pair of all the source IP, destination IP, and then it will apply a reduce operation, like a map, and then a reduce operation. So distinct followed by reduce was what was required there. In this case, for OpenSketch, like, it is using countmin sketch to estimate the counts for different sources. Then it is using a bitmap to count distinct destinations for each countmin sketch counter. And then it is using a reversible sketch to identify the sources in the countmin sketch with heavy distinct counts, right? So as you can see that, it has all the building blocks, but it is relatively complex. As the complexity of the query increases, the complexity of the data structures that have to be maneuvered around to get this query working, that complexity just keeps on growing, right? So in some sense, if there is a good generalization of how these open sketches, the underlying sketches can be generalized for very broader set of queries out there, then I think open sketch will be very, very powerful. And I think like for its time, it was very powerful. But it does offer some limitations in terms of there is no clear sense of what queries can be expressed and what queries cannot be expressed with open sketches, right? So there is a bit more coupling between how these queries will get executed versus how these queries get expressed, right? So the query execution, this is not as interesting bit of open sketch, but just to give you a perspective of how things really work. Whenever a packet is coming in, a packet, they will this pipeline will apply multiple hashing functions for the sketches that we were talking about. Like think about the countmin sketch. So for countmin sketches, you will require multiple hash functions, and then you will apply a classification or a match action table, which will decide that whether you want to do some type of counting for this packet. If yes, then where do you want to update the counts, right? So it has one big SRAM table where you can do the counts. And what it does is rather than having query specific SRAM registers, that was the case in Sonata, where the pipeline was divided into multiple stages and each stage had SRAM. So rather than that, this assumes a data plane model where you have this entire one big SRAM table. And then it has a logical separation between different queries that, like the yellow color is one type of query, the green is the other type of query, and the blue is the other type of query, right? And then it periodically reports these counters to a controller, which then reports these the output of the query to the end user, right? So query execution, as you can imagine, is it is complex, but at the same time, it is still doable. All this type of management through the use. Like you have a open flow controller which can push rules in the match action table, which can do the mapping between the set of flows that match there and which set of indexes in the SRAM table they should be updating, right? And what type of update should be there, right? So some updates can be to do say +1, the other can be to plus some of the value, the other can be like just update the value between 0 to 1, so it kind of like do an OR operation. So these are all different possibilities. Depending on the capabilities of the target, these will or will not incur additional latencies when updating the counts. So query planning problem exists for these type of systems as well. For a single query, because as we were talking about the countmin sketches, so countmin sketches, their accuracy error bounds will be dependent on how many, like what is the width and depth of the hash table, or like width and depth of the countmin sketch that you're taking into consideration, that will have an impact on the accuracy. So what are your accuracy requirements? And based on that, you can configure it. And then for different type of sketches that you're using for a particular query, the complexity of this problem will go. So I don't want you to focus on the encoded representation of this query planning problem, but I want to emphasize that even for a single query, you have like one goal and then 4 different type of constraints that you have to satisfy. And then I think the animation is a bit off, but but this is just for one query, but you have so many queries that you want to run in parallel. So you have to solve an even more complex query planning problem, which is similar to what Sonata was also trying to do, but Sonata had relatively better abstractions to reason about the cost. So its query planning was relatively easier than OpenSketch, but nevertheless, it is a complex query planning problem to work with, right? So this type of, given these type of limitations, it is not suited for handling the network traffic dynamics for multiple complex queries, right? So it is suited if you have fewer queries to run and the traffic does not changes much over time. But if the traffic pattern changes a lot and the complexity of the query that you're trying to run is also very intense, then making it work with OpenSketch is very, very hard. So given these type of observations, another paper that came out was called Universal Monitoring, or UnivMon. And it's based upon a very beautiful theoretical result of universal sketches. and we'll talk about how it addresses some of the challenges that OpenSketch was facing. So the key idea in this universal monitoring system is that it tries to run some sketches in the data plane, but only one type of sketches that it can easily configure. And then it sends the output of those sketches, which are then offline processed such that those sketches can be transformed into the output of specific application that you want to run in the network, right? So think about it this way, that it is transforming the raw packet traces into an intermediate representation, which can then be queried depending on what type of application you're running, what type of like network monitoring application you're interested in, right? So let's try to unpack this a bit more. Let's try to understand what is universal sketching, right? So when we talk about universal sketching, there are these streaming algorithms where you have a stream of length m, where you have m elements, and out of them there are like n unique elements, right? So you can represent that streaming data as a frequency vector, where f1 is the frequency of the first element, f2 is the frequency of the second element, and so on, right? So you can compute frequency moments here. So fk is the sum of fi raised to power k, where k is the order or the moment. So f2, which is the second order, is like AMS sketch or count sketch that we've been talking about. In general, the key idea here is that for each problem, you have a different algorithm for sketching, right? And that's what we saw for the OpenSketch paper as well, that for different type of group by operators, you have to either use Countman sketch, sometimes you have to use FM sketch, for sometime you have to use Bloom filter, etc. But what if you can apply just one sketch, right? One sketching function. Is there any way in which you can arbitrarily use some G function and do a simple universal streaming, right? So that's a question which kind of like was posed in this research, and it was based upon some theoretical results. So the theory of universal sketching, and it's okay if you don't understand the nuances of it. My goal is not to force you understand these theoretical results, but try to build some intuition about universal sketching. So the first theorem is that there exists a universal approach to estimate the GSUM. What is GSUM? GSUM is the sum, like when we look at this function, then for the f of I, which is the frequency, if you apply a function g and sum it over n, then that is called the GSUM of the distribution or of the data stream, right? So to estimate GSUM, when g is a non-decreasing, such that g0 is equal to 0 and g of fi does not grow monotonically faster than fi square. So fi square is what? L2 norm, right? The second order norm. So here, like fi square, or was basically the second order frequency moment, where fi raised to power 2 and the sum is considered, right? So as long as this g is not growing monotonically faster than the fi2 or the second L2 norm of the data, then it is possible to estimate the GSUM. And the universal sketch construction can be used to estimate GSUM with high probability using a polylogarithmic memory, right? So polylogarithmic memory is basically the space footprint, and this is a theorem which says like it is possible to have a universal sketch construction to estimate the GSUM value, right? I'll try to build more intuition as we move forward. But think about it this way, that the informal definition you can think about is that like item I is a G heavy hitter if changing its frequency significantly affects its GSUM, right? So in some sense, like if you can, if you have a data stream and if you can detect that some item is a heavy hitter in that data stream, then if you apply and that is the L2 norm, right? So if you just do the counting, right? If you do a counting on a data stream and you identify that some item is a heavy hitter, if you do the just simple counting, then you can guarantee that it will also be a heavy hitter for the GSUM, right? G meaning like any arbitrary function, which is which satisfies this criteria that it is non-decreasing, where G of 0 is equal to 0 and G of fi it does not grow monotonically faster than fs2, right? So this is the limitation of what functions you can use for G. And as long as that is the case, so if there is a item which is a heavy hitter in the L2 world, the L2 norm case, then it will also be a heavy hitter for the GSOM. And there are two possible cases. One is that if it is sufficiently large, then all the mass, most of the mass is concentrated in this heavy hitter. So it's very easy to detect that a L2 heavy hitter algorithm to find such a heavy hitter is good enough for this case, right? But if it is not sufficiently large, then what you can do is that you will find heavy hitters on a series of sampled substreams. So not the entire data, but you sample the stream over time of increasingly smaller size over time. And then based on that, you try to estimate the G heavy hitter. So let's try to build a bit more intuition here. You have this data stream coming in, and then you generate the n is the number of elements. So now you can generate log n substream by 0, 1 hash functions, where you like selectively take out one of those unique element that you have, right? So in the first case, they have taken out 3, right? And 4 and 6, right? So 3, 4, and 6 have been removed. So given their absence, what is the heavy hitter? Like which of them are heavy hitter in this substream? So it is like a 1 of 1 and maybe 5. Then then in this case, they have taken away 1, they have taken away 3, they have taken away 4 and 6. So now this is kind of like even a smaller set, like this is sequentially built from this set. So now they have here they have taken away 3, 4, 6, which were kind of like not the heavy hitters as such. And then here they have further removed the 1, which was clear heavy hitter, and then they have removed 5. So like you have this sequence of output. You're applying the heavy hitter algorithm, the count sketch algorithm here, and you're computing the L2 heavy hitter for this subsampled stream or substream, and then based on the output of these heavy hitter counters, you're estimating the GSOM, right? So this is the key idea behind universal sketch data structure. And for different applications, you can use a different G function, right? So the first set of pipeline remains the same irrespective of what application, what monitoring application you're running, right? All you need to do is to generate log n substream of the data, and then apply the hash, by using this hash function. Then for each of the substream, you apply the count sketch or heavy hitter algorithm to compute the heavy hitters. And then for those heavy hitters, you apply the G function to estimate the GSOM, right? So this is the key idea behind universal monitoring. And this is very powerful because the first set of transformation that we need to do are agnostic to what application you are running, right? So for all the applications that you can run, you have the same set of functioning or functionality that you need to apply, which is sampling the data, then applying these sketches to do the heavy hitter detection. And then for those top K possible keys, then you apply the GSOM function or the G function to compute the GSOM, right? And then find the G heavy hitters in the network. So let's now try to compare OpenSketch and universal monitoring in terms of performance. What we see in this graph is the comparison of the error rates between the two schemes, right? And here the OpenSketch is using 600 kilobytes per task, right? And the universal monitoring is using around 600 kilobytes total across all the tasks, right? So it is the entire data structure in the data plane is 600 kilobytes, and then it is running, or it can extract heavy hitter, DDoS, change entropy at all of this at once in the user space, right? So the error margins, as you can see, are relatively high compared to OpenSketch, because OpenSketch is dedicating all the resources for one task at all, right? And heavy hitter is trying to generalize those statistics across these different applications. So we should expect universal monitoring to be a bit less accurate or have higher error, which is the case here. But still, the error margin is very small, right? And with the same 600 kilobytes footprint, it is able to run these 4 different applications, right? Whereas OpenSketch is using 600 kilobyte for just one application of one task at a time, right? So if I have to do one-to-one comparison, then the OpenSketch footprint will be around 2400 kilobyte or 1800 kilobyte, because they cannot run the entropy query. So, but like 3 times more state will be required in the data plane to get marginal improvements in the error rate, right? So this is how we can think about comparison between OpenSketch and universal monitoring. And universal monitoring, given its simplicity, is preferred over OpenSketch, and it was a good improvement over this existing system. So with this, we can conclude today's lecture. The key takeaways that we have for today is that network telemetry system have a very rich design space, right? We saw the entire spectrum of design space that we can have for the network telemetry systems. And we tried to place different solutions that we have been covering so far, or what we will be covering in the future in that design space spectrum. The sketch-based systems belong to this broader category of data plane only telemetry system, where you are trying to offload or trying to execute the query entirely in the data plane. The sketches help reduce the memory footprint for stateful operation at the cost of accuracy, right? So compared to Sonata, where there was no loss in accuracy, there is some loss in accuracy for the sketches, right? So this is kind of like their approach of reducing the memory footprint. In case of Sonata, the trade-off was that it was delaying the execution of query, right? So you were running this query iteratively over multiple windows before you can get an answer, right? So that was a compromise for Sonata. But in case the compromise for sketches is that you will compromise the accuracy of the query to reduce the overall memory footprint, right? And both of them are, good and bad depending on what type of queries or what type of environment you're working in. OpenSketch is a solution which tried to develop these, it was first of its kind. So, kudos to that. And then the key idea there was that it was trying to execute these stateful operations using sketches. And for different type of queries, there were different type of sketches that were implemented in the data plane. Universal monitoring leverages the idea of universal sketches, where it tries to just execute one sketch of L2 heavy hitter detection in the data plane, and then tries to apply this G function on this L2 heavy hitter function to extract or to get these values for different type of applications, right? So the type of application that the universal monitoring is able to support is similar as the OpenSketch, heavy hitter, DDoS, change direction, etc. And each of these applications have a different G function, which is applied over the L2 heavy hitter output that is computed from the data plane. All right, so with that, we can end today's lecture. In next class, we'll try to cover the topic of Starflow, which you have read as part of your reading assignment. But now, given this rich exploration of the design space, you might be able to appreciate the solution more. And then we'll try to visualize that solution from the data compression perspective. All right, so I'll see you in the next class. Thank you.